In this video, we're going to take a look at the process of U substitution, but from a slightly different standpoint, because our goal over the next few videos is to kind of mimic what we've done with a single integral when you did a quote-unquote U sub. But we want to be able to replicate that process or extend that process to a double integral and even a triple integral. But in order to do that, we have to look at that old process in a slightly different way. So that's what we're going to do now. Then point out some key characteristics of that process, and then touch on what it's going to look like for double and triple integrals. And then in subsequent videos, we'll get into some of the details. So it will take a little while to get there, even without being super precise at every single step. All right, so here's our goal. Let's write down a typical definite integral, and we know these from Calc 1 and Calc 2. We've used them quite a bit. And normally when you're talking about a U sub, you look closely at the integrand and you look for certain patterns, right? But I intentionally did not write it that way because I want to show you that that U sub process can technically be used whenever, whether it's to simplify or even sometimes complicate an integral. Now you might ask yourself, why would you want to complicate an integral? But here the goal is just that you can apply a very general process to convert this to a new definite integral that will always have the same value, but might be easier or harder to look at, right? So either way, whatever the result is, we can always transform this into a new integral, right? So here's what I'm going to do. I'm going to let x be equal to g of u. Now, here is one point in this video where I am going to be, I'm going to make a huge assumption, right? Even if I drop this assumption, we could still end up at the same place. It would just need a few more details. So the assumption that we're going to make is that g is a always increasing function. So let's assume that g is increasing. And you'll see why in a second. And if you think what this means for the first derivative, if the function is increasing, then its first derivative has to be positive, right? So I kind of want that just to simplify the argument that I'm going to put forth, right? Okay, so right now we can replace the x with g of u. Now there are, I guess you could say, three other components of the definite integral that we need to switch over. I have limits, and I have the dx. Let's handle the dx first. To get dx, I'm going to take the derivative here. So I'm going to differentiate both sides, this time with respect to u, and then I can write that as g prime of u, and then dx, I can put this in differential form as g prime of u du. All right, so now we have the x and we have the dx taken care of. But we can't leave the original pair of limits a and b because those are limits on the x-axis. Now I need to find the equivalent u limits. So let's start with the lower limit. When x is equal to a, what do we get? Well, let's plug a in for x, and we'll have this equation. Now, if I ask you to solve this equation for u, you might say, well, I don't know what to do because I don't know what g is. But here's the interesting thing. If g is has an inverse function, we can take the inverse function of both sides. And it turns out if your function is always increasing or always decreasing, then it's 1-to-1, and you have this nice property of an invertible function, right? So what we do is we take g inverse of both sides like this. Right, now the g inverse, remember, this is not the reciprocal, right? That's different. So when you compose a function and its inverse, right, again assuming that they both exist, the inverse and the original function cancels out. So I'm left with g prime or g inverse of a on that side, and I'm left with the u there. And then if we do the same thing when x is equal to b for the upper limit, so when x is equal to b, what do we have? We have b is equal to g of u. Again, take the inverse of both sides, and we'll have that g inverse of b is equal to u. So now we've transformed the four things that make a definite integral a definite integral. So first, our limits are g inverse of a as the lower limit and g inverse of b as the upper limit. The integrand is now f of g of u, and then the differential, the dx, now becomes, let me put a times there, g prime of u du, right? So I wanted to keep a lot of things positive. I didn't want the derivative to necessarily be negative, so that's why I made this assumption. If we didn't know this, then we would have to look at a couple cases individually, but we could still end up with this result. We might have an absolute value around this, right? Now, so this is a new definite integral, right? And under my assumptions, these are equivalent. I'm just going to take it one step further and just simplify the limits just a little bit. Just rename them, give them different names. Since my original lower limit was a, I'm going to write down I'm just going to say let g inverse of a be alpha. Just call that alpha. And then similarly, let's call the upper limit beta. And then we have f of g of u, and then g prime of u du, right? And there are three key things to note about what we have here, right? The integrand, right, which is our function. So the new integrand is f of g of u. The new interval, right, our interval of integration is u, because now remember we switched over to u, so u is greater than or equal to alpha, but less than or equal to beta. And here I'm just assuming that alpha and beta, the lower limit is actually smaller than the upper limit, right? So alpha less than or equal to u, less than or equal to beta. And then the differential is now, so let's write this down, our differential, our dx, now has this, again, kind of more complicated looking form, g prime of u du. This expression, this g prime of u that's multiplying the du, it actually has a fancy name in its own right, and it is actually called the Jacobian of this transformation. So the transformation x equals g of u, this thing, which is basically its derivative, but it's often called the Jacobian, and it's named after Carl Gustav Jacobi, long name there, but he was the mathematician that actually did a lot of important work on these like transformations. He did it back in the mid 1800s, so like the mid 19th century, did a lot of work. And this word Jacobian is going to come up quite a bit when we get to looking what this process, how this process is going to take shape for double and triple integrals, right? So so our goal is to be able to then apply something similar to double and triple integrals. But let me just draw a picture now. Let me just draw a picture to show you what this means. So if we start with our original graph, remember our function was in terms of x, and let's say a and b are right there. And let's just say that the original function looks like this, right? So this was our y equals f of x. And then we know that that original integral represents this area. All right, we know that much. All right. Well, now with this transformation, a couple things have changed. In fact, a few things have changed. Now, let's say the lower limit is alpha, the upper limit is beta, and then now, so the function here is all of this, right? Including the Jacobian. So if I multiply all of that there, you know, maybe the graph now looks something like this, right? Maybe. And then the area of our new integral, you know, would be like this region. And the principle is saying, or the idea behind this transformation is that these two are equal in area. The regions don't look the same, right? The functions look different. Obviously, there's a relationship. The limits are different, but here, these regions have equal area, right? Now, in double and triple integrals, we're going to have something similar. So for instance, in a double integral, remember the basic way to interpret what a double integral represents is volume. So what we're going to do is to describe a process where we can transform one solid into another solid, a 3D, you know, object, into another 3D object that has equal volume, but one of them will be easier to evaluate than the other. And similarly, triple integrals, right? We're going to be changing our triple integrals in such a way that the solid that we're integrating over, right, is going to be easier in one than the other. And the key to making that whole thing work is going to be something that we call a Jacobian, right? So in this video, I'm not going to define what a Jacobian is. I'm going to delay that to the next video and just focus on the double integral case, where instead of just changing from x to u, I didn't write the u down here, but let me write it right here. So instead of switching from an x-axis to a u-axis, we're going to be switching now from the xy plane. Remember, we were sketching lots of regions in the xy plane into a new plane that we're going to call the uv plane. And then we're going to do something similar for the triple integrals, right? So even though I'm taking a little bit of time going into this stuff, we're still going to be rather loose, for lack of a better word, in terms of the details, because there's a lot of linear algebra or just algebra in general that actually goes into a lot of the theory that we're going to use. But I wanted you to kind of go back, revisit this concept of the substitution, and then hopefully that will kind of set the stage for what we're going to do for the double and triple integrals. So if you're ready to see what that looks like, hop on over to the next video. I'll see you shortly.